Okay, so I can just start. Okay, so Professor Sergio Verdu, who cannot be here tonight, asked me to introduce Roger Penrose. He's giving a series of 3 lectures. In fact, I should remind you that the next lecture will not be here, but rather in Richardson Auditorium on Monday at 8 o'clock. And these lectures are in the context of the Louis Clark Van Nuxem Foundation. So a few words about it. It was founded in 1912 with a bequest of $25,000 and there's a will of Louis Clark Van Nuxem of the class of 1879. By direction of the executors, at least 1/2 of the income of this foundation is to be used for an annual series of public lectures before the university on subjects of scientific interest. Previous provisions were also made for publications of the lectures. Lecturers have included Edwin Hubble, Thomas Mann, James Conant, and Carl Sagan, who talked on extraterrestrial life. Van Nuxem pursued a career in insurance, eventually specializing in insurance law. He died in 1903. To say that I'm very honored to introduce Sir Roger Penrose to give the first in his series of public lectures on the status of modern physics is an understatement. No other contemporary mathematician, I believe, has had a greater impact on overall science than he did. In this respect, he resembles the great mathematical giants of the late 19th and early 20th century, such as Minkowski, Poincaré, Hermann Weyl, David Hilbert, John von Neumann, and Kolmogorov, whose works had a profound influence on physics. Rather than dwell on his long and very impressive list of titles, awards, and distinctions, I will limit myself to mentioning some of his main achievements. Most of them are related to the theory of general relativity, in which no other scientist after Einstein, including the very famous Stephen Hawking, has had as much impact as Penrose. He has made decisive contributions which greatly deepen our understanding of black holes and singularities in general relativity. He is best known for introducing the fundamental concept of a trapped surface and showing that its presence in some region of space-time must bring about the future formation of singularities and therefore the necessary breakdown of the classical relativity theory. His rigorous mathematical result in this respect settled an old puzzle in general relativity concerning the presence of singularities in almost all special solutions discovered in the earliest years of the theory, such as those of modern cosmology, which predict the notorious Big Bang. All such solutions had been found by assuming the presence of symmetries, and many argued that the singularities may be unstable artifacts of these assumptions, bound to evaporate under more realistic conditions. Well, they were all wrong. Penrose's theorem proves that singularities in general relativity are there to stay and thus present one of the most serious challenges to our current understanding of the universe. Indeed, the general theory of relativity is our most satisfactory physical theory, both in terms of its inner mathematical clarity and beauty, as well as in view of its relevance to physical phenomena. If one takes into account Newton's theory of gravity, which general relativity incorporates as a limiting case, it is also one of the best experimentally verified scientific theory. The presence of singularities implies, however, that Einstein's paradigm is incomplete. To be able to salvage some of the most predictive power of the classical relativity theory, even in the presence of singularities, Penrose has formulated 2 highly influential and very intuitive conjectures concerning the nature of gravitational collapse, known as the cosmic censorship conjectures. Nice name. The resolution of this conjecture has become the holy grail of the modern mathematical theory of general relativity. It is widely believed that the ultimate solution to the conundrum we face due to the presence of singularities can, however, only come from a quantum theory of gravity. Finding such a theory is really the holy grail of theoretical physics. Another very important innovation to general relativity due to Penrose is the elegant geometric notion of conformal infinity, which he used in a striking manner to derive the basic law of gravitational radiation. His simple and very intuitive conformal pictures are as conspicuous in the modern theory of general relativity as the Feynman diagrams are in quantum field theory. In addition to all this, Roger Penrose is the initiator of a major mathematical program called twistor theory, whose ultimate goal is to combine relativity with quantum mechanics. Together with Wolfgang Grindler, he has written a monumental 2-volume book called Spinors and Spacetime, widely regarded as a Bible of the field. Even though the ultimate success of twistor theory remains in doubt, it has nevertheless generated, not unlike the more fashionable string theory, a wealth of methods and ideas which have been extremely influential in other areas of mathematics as integrable systems, differential geometry, and topology. Roger Penrose is best known to the general public for his intriguing, controversial, and very stimulating book, The Emperor's New Mind, concerning computers, minds, and the laws of physics, for which he was awarded the Ron Poulin Science Prize book. This was followed by Shadows of the Mind, a search for the missing science of consciousness, and The Nature of Space and Time, his lively intellectual duel with Stephen Hawking. No presentation of Penrose can be complete without mentioning his work on non-periodic tilings of the plane, an interest which he took up as a graduate student at Cambridge. He first discovered such a tiling with 7 tiles and 6, and finally in 1974 he found a non-periodic tiling with only 2 tiles. This looked like an esoteric mathematical curiosity until 1984, when Dan Shechtman discovered an alloy which exhibited a non-periodic crystalline structure. Others were soon discovered. The new materials, called quasi-crystals, were later connected to Penrose's tilings. This is one more example of what Wigner called the unreasonable effectiveness of mathematics, that is, the miraculous way by which pure mathematical constructs, with no apparent relationship to anything useful, turn out to have unexpected connection to what is called reality. No other scientist today is better qualified to address these mysteries than Sir Roger Penrose.
Well, thank you. Thank you very much for those over-generous comments. I always feel a little bit nervous about addressing this audience on the topic which I've elected to talk about. Let's get this machine working first. The title, as you know, is Fashion, Faith, and Fantasy in the New Physics of the Universe. Well, we know that these words would apply perhaps to other areas, and scientists who usually feel, well, it's not like that in science. And ideally, of course, science should be reasonably immune from these 3 Fs, since theoretical ideas are continually subject to confrontation by observation and experiment. Moreover, precise theories tend to be mathematical theories, and there's a very stringent, mathematical theory, it's got to make sense, it's got to be rigorous, it's got to be consistent. And that's a very strong criterion, and you might think it would rule out theories at least which don't stand to hold together. Yet, as regards experiments, often the crucial experiments are not available due perhaps to expense of the experiments or intrinsic difficulty, or quite often it's the case that the experiments collect so much data, just enormous amounts of data. This is true in particle physics, and I think it's becoming true also in cosmology, that there's just so much data that you really have to, it's a theoretical issue to know what to do with it, basically. Who knows what there is in all the information that's been obtained from particle accelerators, which if you just chose to analyze it in a different way, you might find something which is just hiding there, and nobody knows the right way of looking at it. And when you have theories which aren't immediately testable by experiment, as this is true of a lot of modern ideas, then of course the aesthetic judgments can be fundamental and very important. We know in physics that it's often been the case that ideas of what's beautiful have been very important. Dirac was very explicit about this, and certainly his equation with the electron turned out to be very fundamental to physics, and aesthetic criteria seem to be very important. This is a very difficult issue because of the subjective nature of these things. I mean, somebody might think something's beautiful and somebody else not have that view. And so it's difficult to be kind of objective about these issues. So elements of these three Fs can indeed assume significant proportions. I should say that this question of aesthetic judgments is a more subtle thing than what one might call Occam's razor. Simplicity is not really very clear. I mean, Einstein's general relativity, for instance, is that a simple theory or not? Well, it's difficult to write down the equations and very difficult to solve them, and certainly initially very difficult to grasp the crucial ideas. But nevertheless, you still have the feeling that that theory is ultimately something very simple. But, I mean, it's not something you would appreciate necessarily, and it's a bit hard to know, how can you apply these concepts. Certainly it's a very beautiful theory, but how do you judge the elegance of a theory? I mean, how do you know that it's really there? I mean, different people, you might formulate it in different ways, and it's not necessarily obvious that one person's view as to what's elegant will be the same as somebody else's. Okay, well, these issues will be sort of have some relevance to things I want to say. But before talking about present-day physical ideas, let's talk a little about some fashionable scientific theories of the past that today we don't take seriously. There are lots of them. I'm sure I don't know most of them, for the good reason that if we don't take them seriously, we don't sort of learn about them. At least unless we're good historians of science, I suppose, but most physicists aren't. Well, let me mention in particular one of them. This is the theory that the Platonic solids, the ancient Greeks had this sort of view, at least some of them. I suppose it would have been called a fashionable theory in those days. The basic states of matter in the universe were associated with the Platonic solids. Well, I've had to try to draw some of these things here. So here we have fire, which is associated with the regular tetrahedron, and air with the regular octahedron, water, the regular icosahedron, and cube is associated with Earth. And then they found there were 5 of these polyhedra, so they had to think of something that the last one corresponded to. And, well, I think the view that the Greeks had was that somehow the way that the stars and planets and the moon and so on, how the laws that governed them were really quite different from the laws that governed things on the Earth. It really took Newton to appreciate that the same laws applied to celestial bodies as to goings-on on the Earth. But anyway, this was a place for perhaps this other kind of matter, which refers to celestial objects. Anyway, this is sort of Plato was interested in these things. You might think this is pure fantasy, and what's this got to do with science? But it's quite interesting, because I was, in a book I'm trying to complete, I was looking for pictures of these things, preferably signed with Plato, at the end of it. But I gave up on that eventually and had to draw my own pictures. But in some information I got about this, I was quite struck by the fact that it's not just an association like this. There's actually a theory which goes along with these things. And it has to do with how you break these things up and transform one polyhedron into another. And that was related to how matter can transform in one form or another, and so on. So it was quite an elaborate theory of these objects. And maybe in those days it was fashionable, and everybody, you'd be a heretic to take a view that maybe this didn't really correspond to the way the world was. Well, anyway, that's, I don't think many people believe it these days, but it seems like an interesting thing to look at, perhaps. But I've just listed a few other things. The Ptolemaic system was extremely successful for many centuries. I'm not quite sure whether the phlogiston theory and the caloric theory are the same thing or different things. Just shows you I'm not much of a historian of science. Caloric theory, I suppose that meant that heat was a substance. Well, this I think of as phlogiston as something that's basically negative oxygen. But I suppose you could make a theory out of that. Kelvin had the idea that particles might be knots. Sometimes people say, well, they are. And this theory, although it went out, is sort of coming back again. I'm not sure one can quite say that, but it's certainly true that some ideas which may have been fashionable at one time and then fade away and then come back again. I mentioned Mie's theory. It's quite curious that sometimes people consider there's a bit of a dispute about who actually first wrote down the equations of general relativity. I mean, I think it probably was Einstein, but some people say, well, Hilbert wrote it down. He was using a variational principle. And what I find sort of interesting about Hilbert's version, well, you see there's the left-hand side, which talks about space-time curvature, and the right-hand side, which is the matter contribution. And Einstein made some comment about the left-hand side being made of marble and the right-hand side made of wood. But in Hilbert's version, the right-hand side wasn't just the energy momentum tensor of matter, it was a very specific theory, which was, it was a theory of everything, in fact. The left-hand side was gravitation, and the right-hand side was Mie's theory. Now, who knows about Mie's theory these days? But in those days, it was a very fashionable theory, which was supposed to encompass all of matter, except for gravitation, which is the other side. So people were doing that sort of thing in those days too. But who's heard of Mie's theory? I don't know. Maybe a few people have, but it's not a very famous idea these days. Okay, well, let's leave that aside and now try and say something about ideas that people are talking about now. But before doing that, I think something I wrote about these lectures did warn people that there's a little bit of mathematics in what I want to say. And so what I thought I would do is get the mathematics out of the way right at the beginning. It's very simple. I'm going to talk about some very simple ideas, but they will be ideas that come back again, basically two ideas, but there'll be things which come back again more than once in what I want to say later on. So I thought it was worth spelling it out right at the beginning. Now this is something very, very simple, but let me just say it. When you raise a number to a power, that, of course, means multiplying it by itself that many times. So a to the b is a times itself, total of b times. Now, you might do this twice. And I noticed in a book that came out recently, it was printed all wrong, because when somebody meant a to the b to the c, which would be this thing over here, it was written this way. You see, you might think that the brackets go either around the b and the c, or they might go around the a and the b. So if they go around the b and the c, that is what one means. And you might say, why don't we mean this one? Well, it's stupid to mean that one, because you just write it as a to the bc. Okay, well, that's a trivial point, that when you write a to the b to the c, you mean a to the brackets b to the c. Now, I just want to make some very basic elementary points, that with large numbers, a to the b to the c doesn't depend much on a at all. It really hasn't got anything to do with a. Well, a little bit to do with a, not much. It's everything to do with c. And in, I think, the third lecture, I'm going to start talking about numbers like 10 to the 123. And the thing is, that number is really e to the 10 to the 123. But I don't write it this way because often one's trying to describe this in a popular lecture or something, and you have to explain what e is if you were going to do it this way. So the point is they're more or less the same thing. Even though e isn't quite very much like 10, there's e there. But if you take e to the 10 to the 100, I'm not sure that I was just trying this on the back of the envelope the other day. I didn't have a calculator handy, but I think it's something like this. The 10 to the 10 to the 123 is about e to the 10 to the 123.2. Hardly makes any difference. Okay, the number, when we come to it, up there, we don't really know that accurately anyway, so you can see that it doesn't make a hoot of difference what the one at the bottom is. Okay, that's just a very simple point. But although, as I say, I'll say something about this later, I want to say something else about these double exponent expressions, which is what happens when quantities like a to the b to the c, in the limit when a and b become infinite quantities. Well, you have to worry a little bit things like that. Care is needed. But the short answer is that everything depends on the value of c. And it doesn't matter a hoot. Now, what b means either. It doesn't matter a hoot what a is, but it doesn't matter a hoot what b is either. At least a little bit of a hoot, but not much. And these are ideas that were made explicit in the work of Élie Cartan. And this actually is a notation, you put infinities in there, that as far as I'm aware is due to John Wheeler, who I hope he might be somewhere around here. That if I write a to the b to the c with infinity in it, so I mean a to the b infinity to the c. So really it's so that's infinity to the c and it's b times that. I hope that's clear what that means there. And you would use this, I mean, what does that mean, you see? Well, that notation is being used for is the freedom in choosing b functions, and these could be, say, the components of some physical field. You're choosing them freely and continuously on some space of dimension c. So you have a space whose dimension c, and you suppose that the field b can be chosen completely freely, no equations on that space. Then you'd write infinity to the b times infinity to the c for the freedom involved in that choice. And this has an invariant, you have to be slightly careful about it, but basically it's an invariant notion. So you might have different ways of describing your fields, but basically the numbers b and c are invariants. But it doesn't matter too much about b. That's the tricky one you have to be a little careful about. But c is totally unambiguous. There's no problem with that at all. Now, one should make a point here that in ordinary physics, one normally has c equals 3. One's talking about fields which could be chosen freely throughout space. And then you would have some field equations which will propagate that into the future. So you just fix everything on at one time, if you like. And that's what it does in the future is fixed by that. So you don't need to have a 4 up there. The space may be 4-dimensional because it's space-time, but all you need to know is what's going on a 3-dimensional space. So you'll have basically things where c is 3 if you're talking about ordinary physics. Now, just the comment here is that if c prime is greater than c, so you might have 2 of these expressions, that is to say a space whose dimension is larger than 3, on which you specify things, and then you find no matter what the b is here, so I've got a b prime there and a b there, doesn't matter a hoot, the difference is all to be seen in the c, and I put 3 greater than signs here, because it really is enormously huger, whatever the b's are. Okay, that's just a comment which will have some relevance in things I want to say later. Okay, that's point number 1, which is all to do with these exponents and so on. Point number 2 is something a bit different, which is the fact that complex numbers are, well, 2 things. One is they're magical, and the other is that they seem to play a very important role in physics, at least in physics of quantum mechanics. And this is numbers of the form a plus ib, where a and b are real numbers, ordinary real numbers, and where I is the square root of -1. And certainly throughout ancient history there was a lot of argument about these things. So were they things you should take seriously? Were they just an artifact? And so on. Well, it's certainly the case that complex numbers provide wonderful insights into mathematics. And let's see, before saying that, I'll just give you the way in which one operates with complex numbers. You plot them in the plane, the real axis going one way, and the imaginary axis going the other way. So a plus ib just has Cartesian coordinates a and b. And there are rules about how you add numbers and multiply them. That's just the geometry. You don't even need to know that for what I was saying. Okay, that's just a picture of complex numbers. I say they provide many insights. Well, here is one of them. Well, let's take the whole thing there. I could list enormous numbers of these things. Complex numbers are really extraordinarily powerful in providing insights into what's going on with real numbers, but this is just one example where one might be concerned with a power series like this, which happens to be alternating signs, but it doesn't have to be like that. And this represents the function 1 over 1 plus x squared. But it only does it if you take x between -1 and +1. If you get outside that range, then the series doesn't converge. Whereas if you plot this function, it just looks like a perfectly ordinary function, no problem about it. It just has a bit of a bump in the middle. And you find that your power series goes wrong. It's all right in this range in the middle here, but it goes wrong outside there. And you can take the various terms one by one and simply add them together and plot them with your computer, if you like, and you see the curves flap upwards and downwards and get worse and worse and worse beyond that line on the outside. So you say, what's wrong with that? Well, why does it flap up and side and down? Why does it go wrong outside that range? You don't see any reason from the look of the real curve. But then, if you know about complex numbers, then you say, well, this function does go wrong at I. I called it z instead of x now. And it goes wrong at these two places, which aren't on the real line at all. But you see that anything which is closer than that is fine, but anything which is further away from the origin than that, the series will diverge. And the reason it diverges is because of the I and minus I, which you simply wouldn't see if you just look at the real numbers. Well, this is a very familiar thing, I hope. If not, well, then that's what it is. It's just one thing that these sorts of ideas do for you, is they make sense of things that are completely crazy like this, you see. You might say, what happens if you put 2 in there, you see? Well, it give you 1 minus 4 plus 16 minus 64, etc., etc. And the answer, according to this formula, if that's the same as this, is a fifth. And you say, well, how can this sum possibly give you a fifth? Well, I mean, there's no way it could if you just add them up. But in a certain sense, deep down, a fifth is in a certain sense the right answer. Now, you see, that's the sort of thing you have to think that, well, I mean, Euler would have had no trouble with this at all. He said, yes, of course, that's the right answer. It's the right answer because it gives you that series and for that function and so on. But it's the kind of thing you have to bear in mind that in a certain sense, even though rigorously that can't possibly be a fifth, there are ways of looking at it, particularly through knowing about complex numbers, to tell you that in a sense, deep down, that is the right answer. Sort of morally, it's the right answer. Okay, well, these sort of things may come back into what I wanted to say before. I should, when I think about it, I shall write this sort of funny C at various spots to indicate here are the complex numbers coming in, and there's some magic associated with them, some kind of mystery out there which is maybe something to do with physics, or is it just something to do with mathematics? That's the kind of issue that one might have to worry about. Okay, well now I haven't really said anything about fashion yet. This talk's supposed to be about fashion. So let me say something about quantum gravity. Now, Carlo Rovelli, who is somebody who works in the subject of quantum gravity, but he works in a particular approach to the subject, which is called loop variable theory. And in a talk that he gave in the International Congress on general relativity and gravitation, which was in Pune in India in December 1997, well, he thought he'd do a little survey. He's not a social scientist, so no doubt one could question the survey and the rigorous nature of it or not, but I'm not going to worry about that. What he did was to look at the Los Angeles archives and find out in the previous year how many papers on each approach to quantum gravity were there. And this was the result of his survey here. You see string theory, 69. Loop quantum gravity, see, he came out second because it was his own approach was to do with loops, and so on. Now, I don't know if you did the survey again, whether you, I imagine you wouldn't get hugely different answer from that. I should also point out that, although I'm not going to say much about it, although implicit in my mentioning complex numbers and so on, is the fact that I happen to be rather in favor of another approach, which in fact Sergio mentioned, which is twistor theory, and you notice there is actually one down here. So if it was done another year, you might find a 0 there, so I'm not going to do that. But this is just rather to give you some sort of feeling for the activity that goes on in the subject of quantum gravity, and the fact that certainly most of it seems to be in string theory. When I say most, I say that advisedly, because if you add together all the others, you certainly get a number which is less than 69, as you can compare. You can tell this is less than twice the number 69. Okay, so it certainly is string theory is something which is fashionable. There's no question about that. Now, it might be fashionable for good reasons. It might be fashionable for bad reasons. It might be fashionable for reasons which not many people understand, and so on. But let me try and address the issue. I think about the motivational ideas behind string. I should say that I've never worked in the subject myself, so you're looking at an outsider's view on this. Whether that's a good thing or a bad thing, I don't know. But it's the only thing I can do without becoming an expert on the subject, which I haven't got time to do, I'm afraid. Let's try and understand some of the reasons, the motivational reasons, and why people do it. So that's really the sort of thing I want to address in this talk. Well, quantum field theory, that's where we start. I'll say more about quantum theory in the next lecture, so let's not worry too much about what quantum field theory is. But it's a wonderful theory which does apply to, well, is it everything or only certain kinds of things? But it's a wonderful theory anyway. And you can sometimes get numbers out of this theory which are extraordinarily precise. Now, this is an example. It may be there are figures now that are more recent than the ones I've got up there. I haven't checked on the latest figures, but they can't have changed hugely. This is the magnetic moment of the electron measured in Dirac units, and you notice that the theoretical number is 1.001159652, and then there's some uncertainty in the figures here, at least there was at that time. Or you can take the observational figure, which is 1.001159652, and then 93, and so on. Well, that's pretty incredible. So you see that the theory and observation really do agree to this extraordinary degree, which is telling you that there is something very profoundly true, if you like, about the theory. Yet, all these answers depend on having an effective and essentially unambiguous way of dealing with the infinities or the divergences that arise. So what you find is that if you somehow blindly applied what you thought were the rules of quantum field theory, you don't get that answer, you get infinity. And then you have to have some way of getting rid of the infinities and getting this answer. So you see there's a big discrepancy between this answer and the answer that's up here. Well, that's one of the things you've got to get used to in the subject and know how to handle these infinities and so on. Well, one of the important elements in this is a thing called renormalization, which is the method of kind of putting your infinities in nice parcels and putting them into the scalings of certain parameters so that you don't need to know. Okay, the theory doesn't go as far as you might like, and you can't work out what those parameters are, such as the charge on the electron, say. You just have to say, well, the theory is not going to tell you that answer because it's got an infinite scaling factor, and you say, well, if you put that infinite scaling factor into the value of the charge, you said you just work with the observed value, then you can get rid of a lot of the infinities in this way. Anyway, that's the idea. Now, other ways you can get rid of infinities are by using what are called gauge symmetry groups, which can be enormously helpful in ensuring that large numbers of infinities cancel out. So if you have some kind of symmetry in there, which is basic to the theory you're talking about, the dynamics of the theory you're talking about, then you may well find that you can somehow cancel these infinities out. So that's another powerful ingredient. And in fact, in the standard model of particle physics, one makes use of this gauge symmetry idea, and there's the symmetry group, which is written down here. Don't worry about what that means. If you don't know what those symbols are, it doesn't matter much for the purposes of this talk. But what you find out is that you get a theory, this so-called standard model, which is in extraordinarily good agreement with experiment. And it makes use of renormalization, it makes use of this idea of sort of pairing, well, getting rid of symmetries by making use of, getting rid of infinities by making use of symmetries. So it's a very powerful idea. And also, it's a powerful idea in another way, because you say, you know, if you've got a theory which somehow, well, fails to be renormalizable or doesn't have some way of getting these symmetries these infinities to cancel, then it's not got much chance of working. So it's a good selection principle for theories. And the standard model comes about in this sort of way, so that you know that that's a good guiding principle to find a theory which makes sense, in addition to a guiding principle you look out into the world and see what particles are really like. So those things together are what basically drove the standard model to the form that it is. So that's great. But still, it's not the end of the story. You still get infinities, and there are something like 19, I'm never quite sure whether it's 19 or 17, it seems to depend what you read, but never mind, 19 undetermined parameters in the standard model. And you like to have a theory which tells you what those numbers should be. I mean, maybe they all could be anything, but it would be nice to have a theory which gives you some insights into why those numbers, masses of quarks or coupling constants, various things, it would be nice to know why they have the values that they have. And string theory proposes to move forward, and it uses basically two highly ingenious theoretical ideas. So I want to give you some little idea about these theoretical ideas, and they enable one to move forwards definitely from the standard model ideas and get rid of these infinities, or get rid of a good many of them. At least either they do that, or else they give you an indication that it's likely they'll get rid of them. It's never quite clear which is with statement, but let's not worry too much about that. Now, the first thing I want to say is basically the idea of a string, which is what string theory is about, after all. And from strong interaction physics, I should have had a date here somewhere, but never mind, this is some good many years ago now. Strong interaction physics, that's hadrons, well, the forces that hold neutrons and protons together, and so on. Some symmetries were noted which could be made sense of by adopting this string rather than a particle picture. Well, I've really got the picture down here. The idea is that instead of thinking of particles as being point-like objects, and so also it's useful to think in space-time terms, so a particle would then be a curve in space-time. The history of that point would be this one-dimensional curve. Whereas if it's a string, then the history of that will be this tube-like thing, and at any one moment, you see time is going up here, at any one moment you take a section through it, and that tells you what the string is looking like at that moment. So that's the sort of picture one plays with. And notice the C symbol here. It turns out that it's a very useful and beautiful way of talking about these things, to think in some sense of these things being Riemann surfaces. Riemann surfaces are complex surfaces. You have to fiddle around in a certain way which changes the signature. I won't worry about that here, but at least you see the role of these Riemann surfaces. Very, very beautiful area of mathematics, playing its key role in one's studying of these string-like objects. Now, Another feature of this is that whereas the procedures of standard quantum field theory, and this involves what are called summing over Feynman graphs. Well, you see here some Feynman graphs. My time goes up the picture, so you have to think of one particle going along here, another one here, and it's exchanging a photon or something like this. Here, these two particles are annihilating and become another particle and then producing two more and so on. Or they can do more complicated things like this. And in the standard Feynman approach to quantum field theory, each of these things is an integral. If it's one of these, you get a well-defined one. If you have a closed loop, then you're going to get infinities and so on. That's the sort of thing you've got to worry about. And then what you've got to do is take all of these and add them all up. Well, why you do all that has to do with the rules of quantum mechanics, which I'll say a bit about next lecture, so we won't worry too much about that here. But what you find is that two things here. One is you may well get nasty-looking infinities, and the second thing is that you don't see these strange symmetries which seem to be parts of strong interaction physics. Whereas if you write these things in the string way, it's really very, very beautiful. Instead of having these lines like this, they're all tubes. And then you see, looking at these two diagrams, for instance, that they're really the same. Whereas here they don't look the same at all. When you're over here, okay, it may be a little thinner this way and thicker that way, but that's not too important. They're basically the same diagram. And the symmetries that seem to be present in these strong interaction physics could be revealed in this way of looking at things. And the things which should give you these nasty infinities in standard approach, you just have a different topology. And these are the Riemann surfaces that the complex analysis is a very powerful way of talking about. So this is all very beautiful, and there's no question about that. I don't deny that at all. Now what about the other ingredient? The other ingredient is what's called supersymmetry. Now, I just have to say something a little bit faintly technical. These things called bosons and these things called fermions. Well, fermions are like the ordinary particles, electrons, protons, neutrons, or the quarks that make up the neutrons and protons, which are, you have an exclusion principle. They're not allowed to be on top of each other in the same state. And in fact, solid materials depend upon fermionic nature of these basic particles. Or you can have the bosons, which are more like the forces, the carriers of the forces between other objects, or the particles of fields like the electromagnetic field or gravitational field, if you try to analyze it that way. And so you have these two families of particles, and they have to do with the statistics too, whether they have what are called symmetric or antisymmetric wave functions, and that's related to the nature of the spin, whether it's an integer or a half-odd integer. Bosons, it's an integer, and fermions, I think. Anyway, this is a very standard part of particle physics, but the ordinary symmetry groups, like the ones in the standard model, sort of churn around the bosons like this, and they churn around the fermions like this, but they don't churn these around together. The bosons keep separate and the fermions keep separate. Whereas the idea of supersymmetry, you have a generalization of the ordinary idea of a group to what's called a supergroup sometimes, and it churns around these things in a much more comprehensive way. And this can be very powerful at removing infinities. So if you were God or something and trying to invent a theory which was you trying to get rid of these infinities, you'd be well advised to put supersymmetry in if you were just concerned with getting rid of the infinities, because you get rid of a lot of them this way. Doesn't mean that that's the way it was actually done, but that's an important thing to bear in mind. A lot of people are very, very favorable towards supersymmetry for that kind of reason. I think they're interested in constructing theories, and if you make it supersymmetric, you've got a much better chance of having a theory which is handleable. However, supersymmetry predicts that every fundamental particle should have what's called a supersymmetric partner, another partner. And if it's one of them was a boson, the partner would be a fermion and vice versa. However, none of these supersymmetric partners have ever been seen. Now, they may be there, it's just that they've not been seen yet. Now, the thing is, even though they've not been seen, the names are already there in waiting for them. For example, the photon, its supersymmetric partner, the photon is a boson, supersymmetric partner would be called a photino if it's found. The graviton would have the gravitino if it's found, and the Z boson is, I think I've got these names right, the Zeno and the Weno for these things. Anyway, we don't have to worry too much about the names sounding a bit silly if the particles haven't been discovered yet. Oh, actually, that's not a very good reason, because some of the names do look pretty silly even when we have found them. So perhaps we shouldn't think too much about that. We know that electrons are there, and the quarks, which make up the neutrons and protons and so on, they've got their supersymmetric partners all waiting, the selectron and the squark. Now, it always struck me as this is an interesting example of a non-Popperian theory. You see, as long as you don't find these supersymmetric partners, it doesn't disprove anything, you see, because you need what's this called supersymmetry breaking to separate the mass of the one. See, initially these things should have the same mass. And you look around at the same mass and you don't find anything like what its supersymmetric partners should be. But maybe because of some supersymmetry breaking system, I won't go into what that means. I'm not totally sure I know what it means myself. But what you'd need that in order to make the masses sufficiently different that we haven't seen the partners yet. And that's the idea, you see. You say, if you haven't seen the supersymmetric partner, that's because we haven't built a powerful enough accelerator yet to find the energy that we would need in order to find the partner. Now, this is the state of things as it is now, you see. As I say, it's non-Popperian because you could say, so as long as you don't find these things, you just say, well, we've got to build a bigger machine and a more powerful machine and so on. And it doesn't get disproved, at least not in this way. There might be other ways of disproving these ideas. But that's the state of affairs as it is. Every now and again you see a report in the newspapers which says some supersymmetric partner has been found. And then, at least so far, that's turned out not to be the case. Well, you can take two views on this. But it's certainly the case that supersymmetry is very much favored by theoreticians in high-energy physics. And I suppose it's because it would be, if they find these things, it would make life easier in many ways. But there's another reason why people like the idea of supersymmetry. At least I should say some people do. And that is because it's at least a central ingredient to modern string theory. The original version of string theory, which had to do with these strong interacting physics, that's been superseded by other ideas. This wasn't initially supersymmetric, but supersymmetry has become a very important part of the development of string theory. So if you didn't have it, then theory would be in trouble. So that's the reason for wanting it, if you like. Now there's another feature that string theory, as it has gone, has emerged, and that is the presence of these extra space dimensions. Now, when I first heard about string ideas, I really thought it was a fantastic idea, I must say. It looked very beautiful, the way you have these tubes and these Riemann surfaces, and you can get symmetries and get rid of infinities and all sorts of things like that. But then I learned it doesn't work unless space-time has 26 dimensions. Well, I said, well, space-time doesn't have 26 dimensions, so, well, that's the end of that, you see. But that wasn't the reaction of some people. They say, well, if it doesn't have 26 dimensions, we'll make it have 26 dimensions. This would involve 1 time and 25 space dimensions. And then these original ideas were superseded by... See, I should say originally they were meant to be to do with strong interactions. That was the version I was describing before. But the newer ideas were that no, it's a quantum gravity theory. And when I put up my list before, that had to do with quantum gravity. So now this has become a gravitational theory, and there's a change in the sort of coupling strength, change in sort of general character as well, but basically the strings become much, much smaller. They become the sort of scale that you need to consider when you're talking about quantum gravity, the thing called the Planck scale, which is something like 20 orders of magnitude smaller than the ordinary kind of scale of fundamental particles. So that's 20 powers of 10 smaller. So the strings are they're now much, much smaller, tiny little things now, much smaller than the scale of ordinary particles and so on. So this has now become a theory of quantum gravity. And there's an even newer version, I should say, which is basically what's referred to as M theory, where you introduce higher dimensional entities, which are called branes or p-branes. All sorts of puns come up there, which I'm not even going to worry about here. And there are also other kinds of objects which come into the theory referred to as d-branes and so on. I won't describe the ideas here, but I just mention here that the number of dimensions has gone up to 11. So you have 10 space and 1 time. Now you might say, okay, isn't this ridiculous? Because space-time doesn't have that number of dimensions. You know, you could see 3 of them out there, and then there's time, and that's it, isn't it? Well, this really goes back to some ideas. I have no idea whether this was ever fashionable in the old days. I suspect it wasn't. But it was an idea originally put forward, I think, in 1919. Originally Kaluza and then Klein came in. So Kaluza and Klein had this idea, very clever idea, that not that long after Einstein's general relativity was to do with gravity, and the idea of Kaluza and Klein was to incorporate electromagnetism also into the same sort of general scheme, but where you had to increase the number of space-time dimensions from 4 to 5. And you say, well, why don't we see the 5th dimension? And the answer is that the 5th dimension is small. What does it mean for a dimension to be small? Well, the analog of a hose pipe is often used here. Here we have a rather crude picture of a hose pipe running along like that. It looks like a one-dimensional thing. But if you take out your magnifying glass and have a look at it, you see, oops, it's really two-dimensional. The surface of this hose pipe is two-dimensional, but since it's such a small radius as you go around there, you might as well consider it as being only one-dimensional. So that's the idea. The Kaluza-Klein idea involves this, and it does actually provide a way of looking at electromagnetism or electromagnetism coupled to gravity, which actually gives you the same answer as you would get if you use the standard Einstein theory, but where the electromagnetism is simply imposed on the space as a field. So it's a pretty idea, but you say, could you ask this, is it more than that? Is it actually going to give us something profoundly different? Well, you see, if you go from the string theory ideas, then you have to say we are led to this kind of a picture. So let's go back to Kaluza-Klein with more dimensions. Well, it's a hose pipe with a good deal more dimensions, but Kaluza-Klein with more dimensions. But now, the original Kaluza-Klein theory assumed an exact symmetry around the hose pipe. So I've tried to draw that in this picture here. That this hose pipe is given as being symmetrical around this. You rotate the hose pipe around its axis, and it doesn't do anything. And what that tells you, or one thing that it tells you, is that there isn't any extra dynamical freedom from the extra dimension. Now, I just covered that little bit up there, but let's reveal it now. It's the question of how much functional freedom is there in the fields that you're talking about in this system. Well, you see, it's because you have this symmetry, which is given to you around the hose pipe, you are still, like with ordinary physical fields, talking about this kind of functional freedom. So this is where these infinities of the age of the infinity, that sort of stuff is coming in now. Whereas string theory, on the other hand, does allow a full dynamical freedom in the extra dimensions. Now, this is actually a fundamental difference between the string ideas as they exist now and the old Kaluza-Klein ideas. And you see that in the functional freedom involved. You see any function or wave function or whatever you're talking about, or perturbations of the space, will involve freedom going around here, which is completely up to you. It's not simply scaled to be constant as you rotate around the host part. So the functional freedom for a 10-dimensional space-time, well, 10-dimensional space-time is this one. As I say, it depends on the space part, so that's 9 dimensions. So you have a 9 up there, which is hugely more, incredibly more. If you're talking about the classical theory, you would certainly have so much more freedom in this higher dimensional picture that there's no chance, it seems to me, that it would resemble the theory that you're talking about in lower, before you introduce this higher dimensional idea. So here's a question now. Why, in string theory, does this extra freedom not swamp everything and spoil any semblance of agreement with observation? Well, the standard string theorist's argument seems to be the following. Now let me try and get this correct here. It uses quantum mechanical principles, and it says that if you want to excite the modes of oscillation in this, well, I'll draw it as a host pipe, but it's really higher dimensions. If you want to excite those extra degrees of freedom, you need a certain amount of energy, E, in order to excite the lowest mode of these oscillations. So if you want to get anywhere with exciting those oscillations, see, quantum mechanics involve these ideas being sort of discrete rather than continuous, and so you have to exceed this basic energy, E, in order to do anything in those extra dimensions. And this is the sort of point that's made. And then the rest of the argument says, however, this energy E is absolutely enormous by normal particle physics standards. Being of the Planck scale, this is the same Planck I was talking about before, Planck scale I was talking about before, but now it's energies now, which by any particle physics standards is absolutely huge, and there's no way in your accelerator that you could get enough energy to excite those extra modes. So it's argued that the extra degrees of freedom are inaccessible by the ordinary physics of the present epoch. Well, it's the present epoch because you go way back into the early universe when the temperature was supposed to be absolutely vast, huge. Then you find these energies would be available, if you like, at that time. But I want to say, is this a valid conclusion? And I have a lot of trouble with this argument. Although E is huge by particle physics standards, it is very tiny by cosmological or astrophysical standards. I should just say, how big is this E? Well, I should go and work it out sometime, but it's probably like a terrorist bomb or something like that. Okay, that's nasty enough, but on cosmological scale, that's absolute chicken feed. So this energy is not big if you're talking about cosmological scales. And that energy, if you could inject it into the system, would be enough to excite that mode over the entire universe. So you think of the entire universe, you think that's the framework in which you should be thinking. That energy is tiny. So it's more likely then than a particle physics type of interaction, that's perhaps not the right way of looking at it, will be some nonlinear instability in the space-time geometry. And is that nonlinear instability, it might be there, going to be something which could excite this energy? You've got the whole universe to play with and all that little tiny energy. All you've got to do is get that into this extra, that mode to be excited. It seems to me there's every reason to believe that it could be excited. Is there evidence that the 10 space-time geometry might be classically unstable? Well, I think there is good evidence that it is unstable. And this comes from a theorem that Stephen Hawking, actually you referred to in your introduction. Stephen Hawking and I proved several theorems designed actually for 4-dimensional spacetimes, but they apply perfectly well to 10-dimensional or 11-dimensional spacetimes, and they indicate, they whether you say they absolutely rigorously prove or indicate, well, it's somewhere in between those, I would say. It's a pretty strong argument. One could do better, I'm pretty sure, if I had more time to think about it. I think one could do a lot better than that. These things really do seem to tell us that the higher dimensional spacetimes really are unstable, certainly classically unstable, and then you have to see how good an indication that is that they're quantum mechanically unstable. And I think it is a good indication, but then one could argue about these things. Okay, now, if you just stop there, you see, you might say, well, why do we take string theory seriously? Because after all, it's telling us we've got to have all these extra dimensions, and all these extra dimensions are likely to be horrendously unstable, and why should it be so popular? Well, okay, let me try and say why it is, at least I think why I think it is. And we can then start to think, are these good reasons? What are they really telling us? Now, I only can concentrate on a very small part of the whole subject, but I want to concentrate on a rather striking part of the subject. Now, I'm calling this mirror symmetry magic. This actually has to do with the sort of M-theory version of strings. And this led, I suppose, Witten originally made some suggestions here, and then these suggested that the manifolds, these are things called Calabi-Yau manifolds, which were in the hosepipe picture. I had a circle going around the hosepipe, but if you want to have 6 dimensions or something, or 7 dimensions to curl up into a little tiny ball, then you've got more complicated things you might do. And the way in which people like to do this, for various technical reasons, is in terms of what are called Calabi-Yau manifolds. And I don't want to bother you with what they are, but there are these interesting, mathematically very interesting manifolds, structures, spaces, and people have been interested in them for some time. And there are various questions you can ask about some of these spaces. And one of these is the question of counting what are called rational curves. Well, a rational curve is basically a Riemann surface, which is a sphere topology. Don't worry too much about that. But it's counting these curves of a certain kind. Complex curve. The C should be appearing in these pictures here. And there were some calculations done by a couple of Norwegians. There are these spaces, and there's a whole family of them. There's the first one, the second one, the third one. And in each of these, you can count how many of these rational curves there are. Well, these people counted them in the smallest one, and they came up with a number 2,875. And the next one along, they came up with a number 609250, and the next one along 2682549. 425. Well, then, using these ideas of mirror symmetry, Philip Candelas and his collaborators produced this family of numbers. And you see the first two are the same. The third one is different. Now, apparently, you see, the ideas coming from string theory said these numbers should be the same. But they weren't mathematical statements, they weren't proofs of anything, and so the mathematicians tended to say, well, that's very interesting that you got the first two right, but it's only a conjecture after all, so why should you get the other one right? I mean, you don't believe that. But then, I suppose after being tested a bit, they went away and looked at their calculation, and more specifically the computer code that they'd been using, and found, whoops, there's a mistake here, and correcting the mistake, they came up with this number. So this says, far from being a kind of sloppy old physicist conjecture, this is a jolly good way of doing it. And in fact, Philip Candelas and his collaborators, they went ahead and said, well, look, we can do a few more numbers for if you like. And so they come up with all these ones here. So, okay, I'm not quite sure to what extent these things are fully proved, but it does seem, although originally it's a conjecture coming from ideas of string theory, and there's something magical going on there. Well, another point is that mirror symmetry seems to involve the swapping round of what are called Hodge numbers where real and complex parameters get interchanged. So you have some numbers which are naturally complex numbers and they get swapped over for other numbers which are real. And it seems completely crazy that these things should really be symmetry. Something seems to be going on behind the scenes where quantum field theory or string-like entities, of string-like entities, reveals some kind of hidden symmetry involving these complex numbers, which is mathematically true. So there's something going on there, but what is it telling us about physics? And there's a big enigma, it seems to me, hiding there. I think I'll end by giving you a couple of quotes. Now, the first one was some time ago, was given from Ed Witten, and he was obviously very impressed by, I suppose, other things at that time. It is said by Daniele Amati that string theory is part of 21st century physics that fell by chance into the 20th century. And it's that kind of statement, I think, which fired people up to think, well, why do we work on this subject? Now, in trying to finish writing a book that I've tried to address some of these issues and try to learn about them and find out what's been proved and so on, one of the people I wrote to was a mathematician, a pure mathematician, who seemed to know about these things and what was proved and what wasn't, and he was very helpful. Told me what was established, what wasn't established. And then when he finished saying that, he said, well, look, I want to express something. And this is a sort of, I've not put the whole thing down, but this is what he basically told me. Physicists, by which he meant string theorists, find that certain huge dualities between completely unrelated areas of pure mathematics would have to hold. They just say, well, look, the string theorists say, these things have to hold. These can't be coincidence. I can't emphasize enough how deep some of these dualities are. They, I suppose, constantly surprise us with new predictions. They show up structure never thought possible. Mathematicians confidently predicted several times that these things just weren't possible. That they couldn't be, they're just not the right kind of thing, they just can't be true. But every prediction made, suitably interpreted mathematically, has turned out to be correct, such as the ones I just showed you. We have no idea why they're true. They must come from a higher reason. I think this is stating very much one of the reasons that gives string theory its life. And it comes basically from the mathematics community. I've often found this. People say, well, these ideas, we get them from string theory. We had no idea these things were going to be true. They turn out to be true. And if they're people who maybe don't know particularly much about physics and so on, and I've certainly heard them say this, they say, well, look, these ideas come from physics. They give us mathematical things we had no conception of. Therefore, I believe the physics must be right. So the physics, the criterion one sees are these mathematical criteria, and they're telling us something deep is going on out there. Now, what's the answer there? You see, I can't tell you the answer because I don't know the answer. But the question really is, to what extent is it fashion that's driving string ideas? To what extent is it genuine physical motivations? Well, I don't think it's genuine physical motivation. I'm speaking from my own personal opinion here. Because I think that the theory as it exists, the string theory as has been presented to us, or the M theory, doesn't really hang together as a theory, and I don't believe that it can be physics of the future as it stands. I don't believe that it can be, certainly I don't think it can be quantum gravity. I have lots of reasons for worrying about that. I don't think it's a theory of quantum gravity. But I'm jolly glad people are doing it, and it's very likely that it's not just mathematics, that there is something deep in physics which is sort of being revealed by these ideas. I think this is quite a powerful statement here. And moreover, the sort of ideas which go into this, well, what is it that's gone into it? Well, in the statement here, you see, it's something like this, where you combine the ideas of quantum field theory with some of these string-like entity ideas, there is something deep going on there. And it could be that's just accidental, and it's nothing to do with physics at all, and it's okay, some magic mathematics which is going on behind there. And in fact, we know this kind of thing happens. If you take the great thing that Andrew Wiles did in proving the Fermat-Last theorem, that had to do with comparing two systems of numbers, and you see these numbers are always the same. And then, okay, you can find out a reason why they have to be the same. But it's something rather similar. You see with these numbers here, you have numbers which are the same, and there is a reason. There's a mathematical reason why they're the same, but is it telling you something deep about physics? Well, as I say, I have to leave you this. I'm not coming to a clear answer. I think it very likely is telling us something deep about the physical world, but I'm not sure what. I don't think it's telling us that string theory or M theory as it is now is right. I think it's an indication that it might be a good thing to pursue going in that direction and seeing what really is going on and what is it that's being revealed here. Whether that justifies the lists that I gave you early on, if I can find them now, which I'm not sure I can, of the different approaches to quantum gravity, I have a lot of trouble with that. I worry that string theory kind of, as in the world as we see it at the moment, or world of physics as we see it at the moment, it seems kind of to be pushing all these other ideas to the side, whereas I think we need input from other ideas. And I really feel that there is too much activity on the string side, particularly in quantum gravity, and it is too fashionable. But on the other hand, it's something that I want to see. It's another question. Which department should it be done in, you see? Is this mathematics or is it physics? So I think these are questions. I think I'll just leave it like that because I don't have a clear answer to these questions, and maybe it's a good point to stop and people can think for themselves as to what the right answer is.
Everyday energies?
I think it basically is that the numbers are just way out of range. I mean, certainly those energies are out of the range, way out of the range of any accelerator. So there might be some indirect way of experimentally testing these things. And for example, one idea that's been put forward is that maybe some of the dimensions aren't that small, you see, and they might be, a millimeter or something. And that would make a difference to the inverse square law, and that would be testable. I think the situation is really that if they were lucky, you see, and some of the dimensions were that big, then maybe you could see them. But if you don't see them, it's again this sort of Popper business. If you don't see them, it doesn't shoot anything down. So I think the problem is to find some criterion which really tells you that the theory is wrong. Now, the trouble is that it doesn't really, all sorts of places it doesn't make predictions in, you see. It doesn't make much of a prediction with regard to whether gravity should be modified at certain scales. It doesn't say much about what the particle physics spectrum should be, because one of the aims of string theory is also to say something about what, how you go beyond the standard model, and do we see some features which are not predicted by existing theories and which would be predicted by string theory. Well, it's nowhere close. You just don't get that kind of a thing. So the theory as it stands just isn't geared to producing observations. I'm not saying that people haven't tried, because they do. But apart from that, I'm not sure I can give you a good answer. There's some right here.
Yes, excuse me.
Yes.
You had the first two calculations were the same.
Yes.
The third was different. But did the alternative...
Oh, yes, I'm sorry. I was trying, maybe I didn't explain myself very well. That number was changed. They found they'd made a mistake. That is, the mathematicians had made a mistake. I'm sorry about that. It was the mathematicians who made a mistake. And it was not that they'd made a mistake in their calculations, you know, multiplying numbers together or something. It's the computer program. They put on a computer a program to try and work out these numbers, and somewhere in that program was a mistake. And that mistake, when corrected, gave the same number as the string theory argument. So that's the way around. I'm afraid, yes, it's for mathematicians, one might like to have seen it the other way, but... Sorry? The two Norwegians had they'd made I don't know if they had or whether they'd given the computer calculation to somebody else to do. I have no idea. But there was a mistake in their calculation, yes.
You discussed a few theories that had many dimensions of time or space, but are all of them with one time dimension? And if so, is there any explanation?
They're not all. In fact, I didn't mention it, but there's a thing which is called F theory. M stands for all sorts of things, but I think one of the things it might stand for is mother, you see, the mother of all theories, in which case you might consider the father of all theories. So there is a thing known as F theory. Well, when I say there is a thing, I mean there isn't even an M theory, really. I mean, it's not a theory as it stands, but there isn't an F... I mean, to that degree, there is a sort of F theory. And in F theory, there are two times. So it's got, let's see, that's 12 dimensions altogether, 10 space, and 2 times. But I think having more than one time creates all sorts of other problems. And so, well, yeah, I could see some other questions. Back there? Yeah.
Does the quantum gravity remove the singularities that you found? Does the quantum gravity, you expect it to remove the singularities from ordinary general relativity? Or, I mean, so you're running out of...
If you're here on my Wednesday talk, I'll address that question. But the short answer is, I don't think it should. People try, and in loop variable theory in particular, there is a suggestion that they can get rid of the singularities in their approach. But I personally, for reasons which I'll explain in lecture number 3, I personally have considerable qualms about that. It seems to me that that's not necessarily a good thing to do. If you could do it, would be bad news for the theory rather than good news for it. But I'll explain that.
How about the other way? Will the...
How about...
Will the quantum mechanics remove... will general relativity remove the quantum mechanical singularities? Field theory singularities.
I'm sorry, I missed just the end of what you're saying.
Well, there's two fields full of singularities, which is strange.
Oh, I see.
Will one of these fields help the other, I guess? Will you remove the quantum singularities with general relativity?
Well, it's usually thought that they're two parts of the same problem, because the singularities which occur in quantum field theory, or the infinities, certainly it's the point of view in string theory that these would be removed once you introduce the gravitational interaction, or basically when you introduce strings. But the point is, the claim is, and this is an idea that goes actually back to Klein, of the Kaluza-Klein, the same Klein, who suggested that, you see, a lot of the infinities that you get in quantum field theory, the major ones, come about from large momenta, which means small distances. So if you change the nature of space-time in some sense, when distances get very tiny, then that might supply a cutoff to these infinities. And so the idea is that by introducing gravity, that at these very tiny lengths, the Planck scale, will change the structure of space-time, and so instead of getting the infinity, you get a cutoff. Right. So that is... In fact, yes, it's saying these infinities might go to... Well, that's getting rid of the infinities of quantum field theory. And the idea, the other end of the side of that coin, is to say, well, you apply the rules of quantum mechanics to try and get rid of the singularities of general relativity. Well, I think there's something right in that, but it's probably not quite that.
But would that mean that quantum gravity, as we understand the quantization procedure, is not good enough to to deal with this problem.
Well, my personal opinion is, I'll say something about, I have to get straight my lectures, that's the next one, yes. My personal opinion is that the rules of quantum mechanics will have to change for more than one reason. And they do change when gravity gets involved. So I think there are reasons for believing that. And so that's, if you like, more to the point of the answer that I think these questions have, that when you actually bring gravity in correctly, the rules of quantum mechanics will also have to become modified. But that's something I'll try to say something about next time.
Any other questions? Yes.
Hold on a second.
Yeah, you made this argument about how sort of cosmic energy scales were great enough to excite the, let's say, the modes in the highly curved spatial dimensions.
Yes.
And then you made this additional argument that you would think that would lead to space-time instabilities. First of all, I don't really understand why that would be true. Second of all, even though these energies are available, it seems like they would probably only be present around a black hole or something like that. And aren't those objects that are, aren't there space-time instabilities
and the point
in
I
a
was trying
black
to make
hole
is
anyhow?
that,
So I mean, just because that amount of energy is sort of present in the gravitational energy of the Earth doesn't mean that you can excite excitations at that energy scale.
I think one of the questions is, what kind of physics do you apply to the situation? Is it valid to consider the classical space-times, you see? And the theorem that I was referring to has to do only with classical space-times. Now, you see, you can make a kind of qualitative argument to say that in fact, you're disturbing that extra dimension. See, if you just excite the lowest mode, since that extends over the entire universe, you have a certain amount E of energy to excite that mode, but that excites the mode over the entire universe. So it involves an infinitesimal change in the nature of that extra dimension. So it seems to me that you really are in a classical regime. I mean, it's a question of what the right physics to use there. Okay, these things that one can argue about and say, this or that, but the theorem that I referred to is in classical theory. So it says, you have to ask the question, is it fair to look at a classical argument to answer this instability question? And if you come to the conclusion that it is fair, at least to give you a good feeling for what's going on, then the claim is that the singularity theorems do seem to tell you that these extra dimensions are unstable. And it's not a question of just nearing a black hole, because it's a question of injecting this extra energy entirely over the whole universe. I mean, it hasn't had to be localized.
Okay, but if that requires so much energy to excite that mode, why doesn't that energy just collapse into the much lower energy modes in the less curved?
This is the lowest.
So
this is the lowest mode.
In that dimension, but why can't the energy convert into modes in the less curved dimensions? In which case, it's not clear to me why the modes in the more curved dimensions would be excited at all.
I'm not completely sure I'm with you here. I don't quite see why you're suggesting those little ones are going to be untouched, that's all. I mean, there's enormous numbers of degrees of freedom there. It's just a question of is the energy, the fact that you've got what's considered to be a large energy, at least from particle physics point of view, is that going to prevent you from exciting any of those degrees of freedom in the small dimensions? It's just, perhaps we should leave this aside for the moment. I mean, these arguments, one can go on with the arguments and...
In any case, there will be 2 more lectures, so I want to remind everybody that there is a lecture on Monday, 8 o'clock, Princeton Auditorium, and then on Wednesday also at 8 o'clock. So more questions? At 4:30, I'm sorry.
Can you use the microphone? We can't hear you. Where is the microphone Monday?
So the Monday, there is...
Where? Use the microphone. We can't hear you.
Yeah, okay. So Monday, there is a lecture, the second in the series, in Richardson Auditorium at 8 o'clock, right? And Wednesday, I'm not so sure. Wednesday is at 4:30. And Makash, okay, so yes. Makash 10 instead of Makash. Yes.
Yes. When do you suppose what?
Okay.
The question had to do with when are we going? You said the mass of the electron was the question.
Oh, any one of your 19 parameters.
There's absolutely no indication, as far as I can see, that any one of these theories has anything to say whatsoever about what's referred to as, let's see, what is it, the hierarchy problem, which has to do with why the Planck mass is ridiculously of a completely different scale from ordinary elementary particles. I think one's going to have to need something quite different from what one sees in these theories. I don't have an answer to that. It's a big mystery. Yeah.
There are so many theories.